Good morning, everybody. How's everybody doing today? Good? Okay, ready to get started? Okay, so yesterday we went through an example of how the data in fMRI could be processed. We went through the general linear model, that SPM, or statistical parametric mapping, which is a software program used for fMRI. SPM employs the general linear model to see or determine activation regions in the brain that are assumed to be neural activity due to changes in a task or cognitive function. So today what we're going to do is we're going to go step by step through an example of a data set. We're going to look at this, then after this we're going to look at how statistics or computation is used to address a problem of fMRI data. We're just going to go through an example of that. And then we're going to talk about fMRI and MRI safety. And when we talk about that, we'll be watching some movies because there are specialized people who spend a lot of time thinking about fMRI safety and have put together training videos. So I'm going to hopefully play the one that we all watched to make sure that we're compliant with training in fMRI safety and MRI safety. Okay, so we'll get started. So yesterday, and the past few days, we've talked about fMRI data all the way from the raw Dicom images to the first level analysis, which is single subject analysis, to find regions of activation in a single subject. And then we've talked about second level analysis and how some of these activations are combined across groups of subjects. So today we're just going to go through an example of a single data set. And this is just one that I randomly chose from our data sets. So in compliance with our laws in the US, every time we use data, it has to be de-identified completely. So nothing that could identify any markers of a participant in research. So this has no identifiable information. I don't know if you have such laws here in India for medical privacy, but in the US they're very strictly enforced. And sometimes our Institutional Review Board, which is our IRB, will come and audit our studies just to make sure we're in compliance with not only our protocol and what we say we're going to do in our research, but also protection of human subjects and privacy issues. So that was just a little bit of a beginning to looking at this data set. So what we do initially, again, is we collect the data, and we take the raw data and we convert these Dicom files, which are the raw data that comes directly from the scanner. These Dicom files have already had the two-dimensional spatial Fourier transform employed, so they are actual image space data. And we take these and we convert these to what we call NIFTI format, which is a format that our programs can read. So this shows on the left the anatomical scans and on the right the functional scans. And I will be talking a little bit more about what task we use to collect these in a few minutes. But this shows what the images might look like at the very first raw level after we take the raw files and convert them to image files. That would be step one in our processing. Now, the data set that I'm showing you here was taken in a block design. So if I had taken it in an event-related design, we would do slice correction first, which again is taking into account the fact that all the slices are not collected at the same time because it takes a few seconds to go all the way through the head. So in that case, to line up all the timings according to the task, we would move those later slices back to the starting point. But we don't do this in this because it's block design. So our first correction in this is motion correction. And motion correction is perhaps one of the most important correction steps, because as I mentioned before and previously, if we have motion in our data, we may be attributing activation or intensity changes across time to motion rather than to the actual cognitive task that's happening in the brain of the participant. So for our motion correction in SPM, we do a two-step procedure. First, we register all images to the first image in the scan series. So what registration means is that we take every image in our time series, and remember we have an image. By an image, I'm talking about both the X, Y, and Z. So our image is actually a three-dimensional stack of slices in the head. We're taking that and we're taking the first image in the series and we're wiggling around all the other images to line up, and we have an optimization algorithm that looks for something, for example, the difference maybe between the means, just for a conceptual example. So it wiggles these all around until they line up to the first image in the series. So after we do that, we then take this entire series and we compute an average of it. So we compute a mean image. And then our second step is to go back and register each image in the series again to this mean image. So again, we take the first image, we line all the images up to it as best we can. Then we compute a mean, and then we line all these images up again to the mean image. Now, this is not necessarily done, this two-step procedure, in all cases of fMRI studies, but this is an option we have in our program. So we use this two-step procedure just to be on the conservative side so that we have adequate motion correction. Okay, so after we've done the motion correction, we end up with 6 parameters. And remember, these are over time because we have a time series of images. So the important thing to do after your motion correction process is to actually look at your motion estimates. So if you can see here, the top plot shows the translation. So the translation is the movement in the plane, either in the X, Y, or Z directions. And you can see here that these image parameters are correlated with each other, meaning they don't move independently of each other. If something moves in one direction, a lot of times it also moves in the other. People don't generally move in a straight 90-degree or orthogonal fashion. So if you're moving, sometimes you're tilting or going this way. A lot of times, as the participants relax in the scanner, they'll start to drop their head down more towards their chest. So we tried to minimize this by making sure that they're comfortable and in a position that they think they can maintain for an hour when we put them in the scanner. So we tell them, make all your adjustments and movements now so that you're completely comfortable in a way that you can maintain for the next hour without moving about. So in this case, the motion is actually in millimeters. And for reference, one voxel in our study is about 3 millimeters. So those voxels are those little chunks of tissue that we are dividing the image into. And each voxel has a uniform intensity, if you remember. So this person moved, the maximum was about 1/3 of a voxel that they moved. So that's pretty good. We tend to say if they move more than a voxel, we can't use the data. So we look at this the y-axis here, and if we see big numbers here, we just throw the data set out. We can't use it at all. The bottom is the rotation. So again, this is also correlated with the translation because a person very rarely just moves one direction or one rotation at a time. Usually if they move their head, all the directions are affected by this. So just to give you an idea of the rotation, it has pitch, roll, and yaw. So the pitch is the shaking the head in a yes direction. The yaw is shaking in a no direction. So I always think of an airplane that if it goes like this, it's a yaw. and the roll is this way. So we looked at the motion estimates in this data set and we said, okay, this looks reasonable, so we're going to keep this data set in our study. The next step is anatomical to functional registration. So when we do this, we generally take the mean functional image, which you can see here on the left, and we line up the anatomical image to this functional image. The reason we line up the anatomical to the functional rather than the functional to the anatomical is because the less that we resample our functional images, the better quality we're going to maintain. So if we start moving our functional images and we've already motion corrected them, so we've already resampled them once, the more we resample this image, the more we're smoothing it out and degrading it. So we want to try to keep from moving it as much as possible. On the other hand, the anatomical image, we're not doing this analysis over time, so we can move that slightly without causing big problems. So to register these, it's a minimization of an objective function. The one that's used here is called normalized mutual information. So again, we're wiggling this anatomical image around till we find the best match to our mean functional image. The next step is normalization into Montreal Neurological Institute, or MNI space. And to do this, SPM does something that's sort of unique here. It breaks down, okay, so I should say first of all, the image that's normalized to the MNI space is actually the anatomical image. So this anatomical image in SPM is first broken down into white matter, gray matter, and CSF. So that's called segmentation into different tissue types. And then it takes these and it aligns them to the MNI brain. And you can see here the different tissue types that we've had segmented from. Our anatomical scan is on the bottom left, bottom right, I'm sorry. On the top left is our gray matter. The top right is our white matter. The bottom left is the cerebrospinal fluid, or the CSF, and this is our anatomical scan. So once we have aligned the anatomical scan to the MNI scan, we can take those same parameters that we used to move this anatomical scan to match the MNI brain and apply those to our functional images, because our functional images are already lined up to our anatomical. So everything is moved as a single process into MNI space. That is, the anatomical and the functional images are put into MNI space using the same parameters. Okay, so this is after we've taken our images and normalized them to the MNI space, and we do another quality control check here. We look and see how well our images match up to the MNI space. So if you see the top images here, the left and the right top are the anatomical and the functional respectively, and on the bottom here are our MNI brains. So the MNI brain here on the left is a single subject 27 brain. If you remember, that single participant was scanned 27 times, and this is an average of their single brain. On the right here, I believe, is the 152 brain, so that's an average of 152 people's brains. So we take our images then, and we typically check the landmarks of the images. So we compare the borders of the head to the borders of the MNI space. We compare the corpus callosum, which again is the big white matter in the middle that you can see very well on the sagittal image. We compare that to our person's brain. And generally it does a pretty good job. It's sometimes it'll be off just slightly, because really all brains are different shapes. All ventricles inside the head, which is this fluid-filled space, have different shapes, but they're approximately the same. So we check to see how well it did. So we can see here on the top, again, are our images, and we see that they're fairly well lined up to these MNI brains. So in some cases, the optimization program will do a poor job. So it'll squish the brain up in the front, or it'll come up with a really odd shaped brain. And we take steps then to try to do a better job. And we can do this by moving our participant's brain into a better starting location for the program. So we may take our brain from our participant and line it up in a way that we feel like the program will have a better starting point, so it can do this normalization process in a better way and end up with a nice match between the brains. So this shows the before to the after of the normalization step. So on the left here are our single subject's brain, and on the right here is after we have put it into MNI space. So you can see a couple things have changed here. It's not exactly the same slice anymore. So, and looks like our person's brain has been blown up a little bit to match to the MNI brain. The person's brain was initially tilted a little bit, and sometimes this is because of the orientation of their head when they're in the scanner. But after our normalization step, it's lined up and adjusted this way and warped to match the head of the MNI brain. Okay, our next step is data smoothing. And on the left is our functional image after it's been motion correction, co-registered to the anatomical, normalized, and now smoothing. So you can see on the left is a crisper brain. On the right is after spatial smoothing. And we used a 6 millimeter Gaussian smoothing kernel for this. People often use 8. And we tend to try to be a little more conservative in how much information we smear around. So we stick to 6. So it's about 2 voxels, just as a reminder. So we're sort of smearing this information between 2 voxels. Okay, then we're all done with what we call pre-processing. So this is all the processing that we need to get to the point where we're going to do our data modeling. And again, this modeling is going to be first level analysis. So to do this, we first of all need to know what our task design was. This is very important. And what we're looking at actually here is the block design faces task that I showed you the other day. We're going to see it again briefly so you can be reminded of what this is involved with this task. But we have 4 conditions in this task, so it's fairly simple. We have the person looking at blocks of angry faces, blocks of neutral faces, blocks of fearful faces, and blocks of control figures, which are those bathroom sign figures that we saw. So to do modeling of the data, we need to know the exact timings and durations of each of these conditions. So each of the stimuli the person is looking at. And when we do this task across multiple subjects, we randomize the order in which they're going to see these different emotions, because we don't want to have any results that are dependent on the order that the people are seeing. So just to eliminate this potential introduction of some kind of a non-randomized effect, we show the people the different faces in different orders. So a reminder, the faces task that we looked at is the implicit emotion processing. Implicit meaning that they are not actually attending to the emotion. So this is designed to look at a background emotion processing. So the instructions are to the person, pay attention and respond as quickly as possible. If you see a picture of a male, press your middle finger. If you see a picture of your female, press your index finger. And you may wonder how they're pressing buttons in the scanner. We have a specialized glove that they use. This glove is non-magnetic, so it doesn't have any metal in it or anything that would cause an interference with the scanner. And it fits over their hand while they're in the scanner. It has a little belt that keeps it attached to their hand. and it's basically an array of buttons. So the buttons are big and chunky, so they don't have to look at it while they're doing the task. They just press each of these buttons, and it records their response. And we can see it actually in the control room. So we can see what the response is, and we can see if they're making a response or not. Because if they're not responding, then we know there's something going on. And this could be anything from their projector isn't working and they can't see the task at all. We've had that happen, to they fall asleep. So sometimes we'll stop the experiment if they're not doing the task, and we have an intercom system. We can speak to them and we can say, what's going on? Why aren't you doing the task? We can also see them from the scanner room. So we have a big window between us and the scanner room. This window has these shielding metals in it to keep the magnetic field more contained within the room. So there's nickel and copper in the window, so you sort of see a distorted view of them, but you can see them in there. And we try to tell them to stay as still as possible. Sometimes they'll get bored and start kicking their feet around, so we try to tell them, please don't do this, because you may not think it does, but it's moving your head slightly when you're doing this. So we try to keep a good monitoring on our participants as they do this task. Bless you. Oops. Okay, so here's the faces task, okay? So again, we're telling them respond as quickly as possible. Press index finger for female, middle finger for male. So we're gonna see blocks of 6 faces, and within 19.5 seconds, that's the duration of these. Now, I don't think I have the timing exactly correct here. I just wanted to show you the examples. This is what they're actually seeing. Okay, and then the next block, they would see something like this. And that's about the right speed. I think I timed these to show every 2 seconds, which is what they see in the actual experiment. Again, they have the blocks are actually 19.5 seconds, during which 6 images are displayed. And again, these blocks can either be angry, fearful, neutral, or control. So the images are shown on the screen for 2 seconds each with an ISI, that's inner stimulus interval. So that's the amount of time between each image. This can vary from 3 to 8 seconds. We try to keep this random as well, so they don't get start to expect what they're going to see. So we try to keep that variable. And throughout the duration of a run of this, each condition is shown 4 times. So they see 16 20-second blocks during this experiment. And during this time, 165 time points are collected. So a slice of the brain from top to bottom is collected 165 times. Our time of repetition is 2 seconds. So again, this is the time from which the protons are flipped to when they come back into alignment again. They don't necessarily come all the way back, but we're flipping these every 2 seconds. And in that 2 seconds, we're collecting all the images in our brain and getting back to starting point. So if we take 165 total images times 2 seconds each, we end up with a task length of 330 seconds total. If we convert this to minutes, we end up with a task that's 5 minutes and 30 seconds long. So that's about a pretty good time. A person can generally attend to something for 5 minutes without getting too bored. But in this case, the good thing is that we're showing our images pretty quickly, so it keeps them from getting too bored and falling asleep in there. So we're collecting, actually for this, 37 slices every 2 seconds. So we are actually collecting, if you see on the bottom, 18.5 slices per second. So that's pretty quick going through the brain. And if we compute 165 time points, times 37 slices, we end up with over 6,000 slices total that we've collected. So a run sheet for our study may look something like this. This is the information that we would give to the MRI tech, or the information they would be looking at while they're running our scans. So when we do human subject studies, we have a radiologist technician who actually runs the machine, and usually then there's somebody from the lab who is talking to the participant, telling them what's going to be coming, and running basically the functional tasks as the scan is going on. So again, we have one person just running the MRI machine. We have the other person attending to the person and doing all the tasks. So this gives them the complete series that they need to run from start to finish. So when the person's first put in the MRI machine, they have some localizer scans that line up the head in the scanner so that the scanner knows exactly where the head is. So we have a localizer in the sagittal, coronal, and axial plane. Then we do these in-plane images, which is basically our slice prescription for fMRI in an anatomical space. So these are pretty quickly collected. These first 5 steps, we don't typically use the image. These are reference scans that are designed to get everything lined up within the scanner. Step 6 here is actually our anatomical scan. We do that first before our functional scans. That scan, I think it takes, so you see here in seconds, 7 minutes and 2 seconds to collect. This is most likely a spin echo sequence. And again, when I showed you the spin echo sequences, those are the ones that send the pulse. Then the protons are flipped 180 degrees to allow for a rephasing or a convergence of the phases to get a nice, crisp anatomical image. Then we go on to do our reward task, or that guessing task that I showed you when they're guessing the number on the card. That is an 8-minute and 6-second task. Then we do our faces task, and it's actually 5 minutes and 36 seconds. When I told you it was 5 minutes and 30 seconds, what I didn't tell you is the first 3 images that are collected are, we call them distack images. They are performed to get the signal strengths all going well in the brain before the actual data is collected. So those first 3 images are thrown away, and then we use the rest of the series for our functional scans. In this case, we collect a DTI image. We haven't talked about those yet, but we're going to. Our DTI scan is a long scan. This scan is 10 minutes and 4 seconds long. So this is a very intensive scan. As intense, by intense I mean it's really pushing our gradients, the spatial gradients that switch. So in fact, the table shakes due to the gradients working so hard during the scan. So we usually warn our participants about this. They just lay still and relax. It's an anatomical sequence, so they don't need to be thinking anything or doing anything for DTI. But we do warn them that the table's going to shake a little bit so that they don't start to worry while they're in there. This last step 10 was something that we considered adding, but we actually don't do that step. Because the reason is because we try to keep our scan in an hour. We're paying by the hour for this. So we need a few minutes to get the person into the scanner and comfortable and lined up. So we have to consider this in our hour time because we book an hour by table time. So this is the time when the person gets on the MRI table to when they get off. So we have to get them in there, get them situated and comfortable, and collect all our data within the hour. So we take these timing parameters and try to compute how much time is actually taken up scanning within the hour and make sure that we have enough time to get them set up. Some labs don't do this. They try to just maximize their whole hour. Then they run late, and then the person behind them runs late, and the person behind them runs late, and it sort of sets this domino effect of being late for everybody in the day. So you really don't want to start irritating all your co-investigators. So you want to try to keep your times down to a reasonable hour. Okay, so to do our first level analysis, or to find the regions of activation in this single participant, we need to know the onset of the conditions that we're looking at and the duration length, so that we can model when the bold signal will start, for example, for looking at these angry faces, and for how long they're going to be looking at these angry faces. So again, we're going to assume that our bold signal is going to rise in the regions of the brain that are responsible for looking at angry faces, and it's going to keep going, and then it's going to fall after they're done. And in between, they could be looking at this crosshair. So we don't model this part because this is a block design. So they're doing one condition, then they're doing another condition, and then another. So again, each condition is shown 4 times. And we do use our motion estimates for task regressors. I just want to point out with the timing pretty quickly, by looking at these timings, these are all in seconds, you can get an idea of the order that the tasks have appeared, that the conditions have appeared. So our first event is the fear at 9 seconds. You can see in the second row here, and that lasts for 19.5 seconds. So the next one after that would be the angry face, because that starts at 28.5 seconds. Then again, 19.5 seconds later, they see the neutral phase. That starts at 48 seconds. And likewise, then we see the control. The next one they would see would be the angry faces again. So this alternates between these conditions throughout the whole length of the experiment. So we know exactly the times that the person was in each of these cognitive states for further modeling. So we assume that we assume a function for the bold signal, okay, when we do the modeling. So we assume that this signal is going to go up and down, and then we're going to try to fit our intensities to this function, okay? And then we're going to try to line them up in a linear way. So we're assuming that if our bold signal is going up like this and then coming down, that what we're going to see in our data is that it's going to go up like this and come back down. So the voxels in the brain that most closely match this up and down behavior in accordance with the task are the ones that are going to appear as active in our scans based on the model that we give. So the model estimation is done using what's called a restricted maximum likelihood method. And what this does is it estimates our beta coefficients for us. So if you remember, our Y, our bold signal, equals the beta coefficients plus our task predictors, the X, plus an error term. And we also add in there the constant for where our linear model is going to cross the Y-axis. So what this does is this model makes the assumption that the error correlation structure is the same at each voxel. So this means that it's assuming that the way that the error is related to our data is going to be the same for each voxel. So so when we try to figure out how many beta coefficients are going to be estimated with this model, we can say there's going to be one for each of our conditions. So we're going to have a beta coefficient for anger, a beta for fear, a beta for neutral, and a beta for control. Then we're going to have our 6 betas for our motion estimates. So we're up to 10, and then we're going to have a constant. So we know that when this model is done running, we're going to have 11 beta coefficients. So if you remember, this is Y equals beta 1 x1 plus beta 2 x2. So we're going to compute these each for each condition of our task, plus our motion. So what we're trying to do is explain what's going on in each, we're trying to explain why the data is changing, why are bold signals changing in each of these conditions using all of these parameters. Okay, so the data could be changing because of the motion and because of the task. So we try to model that effect for each voxel at the other time points. So yesterday I showed you one of these plots that's generated by SPM to try to explain our model. And today I can explain it a little better because we actually know what our model is. So time is along the y-axis here. It's actually going from top to bottom. And so in the top you see A, F, and C. That is our anger, fear, neutral, and control conditions. And you can see the white spots show where these were turned on and where they were turned off. So again, each of these is shown 4 times throughout our task and for blocks of 19.5 seconds. So you can see anger is shown 4 times, fear is shown 4 times, neutral and control. The X, Y, Z are our motion estimates. Instead of looking at them in a squiggly line, we are looking at them as intensity values over time. So this is X, Y, Z. Our R1, R2, and R3 are our rotation estimates. And C in the last column here is a constant. You could see C is a solid color because it's a constant. It's not changing over time. So again, the bright spots here indicate when the condition was active in our task. Does everybody follow that okay? So after we assign our model and run the program to estimate our beta coefficients, they might look something like this. So here we see our beta coefficient that was estimated for anger, 1 for fear, 1 for neutral, 1 for control. Of course, we could also look at our beta coefficients for all of the motion estimates as well. Those don't interest us as much as these do. So those ones are trying to get rid of the variance due to motion. These ones we're trying to use to see where our activation is for each of these conditions. Okay, so what the model of SPM spits out is also the residual variance estimate. So these are our error terms. This is how much was left over of the data, or how far from the line each of those fit. When we try to model that linear model, remember I showed you, we try to fit a line to it, and there's always that little places where it doesn't line up exactly. So this is our variance. So residual variance, we don't want to have big bright pictures for this. We want to have as little error or residual as possible. Okay, the middle one shows what's called a resolution element. So this sort of describes the spatial image resolution. I am not quite sure what we would do with this. I'm sure some people know, and if you wanted to look into it more, you could probably get an explanation of what it is. These ones we don't typically look at as much as we look at our beta coefficients. SPM also spits out this mask image. This shows where the subject had data. So if we would pull up this mask and we'd see a big black circle in the middle, that would be a problem because for some reason our data wasn't collected in that space. And this could happen if a person has maybe braces or something that blocks the signal out, and we would have a big hole in the front of the brain there. We don't want that. You can see here that there is a little bit of space here in the sagittal slice. Here. That occurs because this is an area where the sinuses are, and there's a lot of tissue variation going on very quickly. So sometimes the collection programs have trouble distinguishing what the intensities really are in these regions. It's due to an error called susceptibility artifact, where it can't really it's having a hard time because the tissue is varying in intensity so much in these small spaces. So this leads to what's called signal dropout. So if we get too much signal dropout, then it's a problem, because if you remember, the midbrain is or the limbic system is very close to this area. So in a task like emotional processing, this is an important area to us. So if we get too much signal dropout in this region, we can't use the data. Okay, so I showed you the beta values, but we know that activation occurs when there's a difference between two cognitive states. So just looking at these beta values doesn't give us a lot of information about activation. What we need now is contrast images. So we need to see the difference from angry to neutral, or the difference from angry into control. So our next step is to figure out how we contrast these images. And the answer to this is that we give weights to each of these conditions, and SPM computes the contrast based on these weights. So here's an example of how we would weight our contrast or our beta coefficients that come out. So we would tell SPM we want to contrast anger greater than neutral. So we are assuming that there's more activation for angry than there is for neutral. So we would give anger a 1 and neutral a -1 in our weights. Say we wanted to contrast fear greater than control, we would give fear a 1 and control a -1. Now, say we wanted to combine anger and fear, and say the activation during anger and fear combined is greater than the activation in neutral and control combined. So what we would do in this case is we would give a positive 0.5 to anger and fear and a negative 0.5 to neutral and control. So if you can see the pattern here, these are adding up to 0 when we're contrasting our parameters. So we're giving them weights based on what we think is going to be higher and lower. Now, another way we can specify this model is to model it to baseline. So baseline, we're assuming, is anywhere in our task that we haven't specified a time for. So in the case of faces, we haven't left a lot of open time. If you could remember, we modeled very quickly or just up snug against each block. So there's not a lot of baseline in this data. But sometimes for event-related tasks, instead of assigning a rest, so they're doing the event, you remember they do single events in event-related. The signal we're assuming is rising and falling. And then this space between that time, between the next stimulus, is what we would call baseline. So we don't always model this time, and we could just tell SPM to take all the timings that aren't modeled and call this baseline. In this case, our signal our contrast weights would add to 1. So if we did anger greater than baseline, we would put 1 for anger and 0s for the rest. Fear greater than baseline, we would put a 1 and 0s for the rest. So again, baseline greater than neutral, so we could assume baseline's greater than neutral. We could put a -1 for neutral, so it's modeled as less than neutral. And then I just put an example of anger, fear, neutral greater than control. We would give 0.3, 0.3, 0.3, and -1 for control. So hopefully that all makes sense. I should have pointed out initially that we're looking at these columns. So anger is in the left column. Those are parameters all the way down: fear, neutral, and control. Does that make sense to everybody? Okay, so if you remember the model, this block here that I showed you from SPM, the time-dependent model, when you pull up these contrasts, SPM will show you the weights of the contrast. So if you remember, the order was anger, fear, neutral, control. And you can see at the top here, it put a positive value of 1 for fear and a negative value of 1 for control. So that will line up to the underlying columns here that we've designated for each condition. In the case of anger, fear, and neutral greater than control, you can see that it gave a value of 0.3 to each of those conditions and a negative 1 there for control. So that's a way you can go through and check that you've specified your contrast correctly in your model by looking at it visually. So how do we estimate the contrast once we have these weights? Well, what SPM does is it creates a linear combination of the beta parameters using these weights. So C prime here is the contrast in a column now. So it's the transpose of the beta weights. And the B here is actually the betas. So what we do is we were going to test that the contrast times the beta weights will equal to 0 in the case of null hypothesis. Again, null hypothesis is the assumption that our cognitive condition had no effect on the voxels in the brain. And we're going to test that against the idea that our contrasts times our beta weights had a difference. So we're that in that case, then we'll be seeing activation in saying this is due to our tasks. So once these contrasts are created, SPM creates what's called an spmT map, and these indicate the T values at each voxel. So these are our contrast images, okay? So the left I show, far left is anger greater than neutral, middle is fear greater than control, and the last one here is anger, fear, neutral greater than control. So I want to point out, by just looking at these contrasts, we don't get a lot of information intuitively, right? So it looks to us sort of like a blob with different intensities. And these are spmT maps. So these are taking our contrast images and making T maps out of these. So again, these are not exactly that useful by themselves. So what we're going to do then is we're going to pull these into our viewing or displaying software, and we're going to assign different colors to the different T values in the maps. So the color bar here shows the T values, and you can see that we're displaying both the positive and the negative T values. So we're looking at the two-tailed t-test. So say we said this is for anger greater than control. Well, the positive values would denote where anger was greater than control. The negative values here would actually denote where control was greater than anger, because it's the flipped effect. So we can see both tails of our t-test here. And by adding color, it becomes much more apparent to which areas were actually active during this task. So the darker red colors show the areas where anger would be greater than control. So this is our software display program. It's called XJView. That's the one that I typically use. This runs again from MATLAB and SPM. I don't know if you guys use MATLAB here, but it's a computational processing software language that we use, and SPM runs on top of MATLAB. So it's a program that somebody wrote to run in concordance with the actual MATLAB software. So XJView will help you look at different thresholds of these images. And I don't know how well you can see this here, but the controls down at the bottom allow you to specify the p-value and the cluster size that you want to see. We're going to look at these a little bit more. So, okay, so we're looking at anger is greater than control here. And we're going to set our p-value to 0.05, which is a fairly liberal p-value. And we're going to select our cluster size to be 1. So this will limit how big our clusters can be. So at a size of 1, we say that we can see single voxels activated, and we're not putting any limitations on how many voxels have to be contiguous together. So we say that any voxel or any cluster that's equal to 1 or greater can be active. And what we see here is we see a lot of little spots and we see a lot of activity. Okay, it's because we've allowed our cluster size to be 1 or greater. So that's a pretty small cluster size. So what's going to happen then if we restrict our cluster size now to be equal to 20? So we still have a low p-value of 0.05. Now we said we only want to see spots that have a cluster of 20 or more voxels that exceed this p-value of 0.05. So we're placing a bigger restriction on these. Again, these we have to have a set of voxels where all the t-values create a p-value greater than 0.05, and there has to be 20 of them all linked together at their borders before we want to see them labeled as active. So you can see here it gets rid of a lot of the little spots here that we see. We still see some spottiness, but not quite as much. Okay, so what if we increase our p-value for the same data set to 0.001 and keep our contiguous cluster threshold at 20? Well, you can see here we pretty much wiped out all our areas of activation. So there's not a lot of areas where the p-value of 20 voxels together was greater than 0.001. And we see on our glass brain here, there were a few spots, but not like before. So if you look at this glass brain before, you can see how much activation we're seeing, both in the positive and negative tail. Here we've wiped out a lot of that. So this is a very conservative threshold for us. Okay, so now what we've done is I've taken the p-value at 0.001 and put our contiguous cluster size back to 1. So any voxel that exceeds 0.001 and a p-value will be shown here. You don't see a lot of them here on the image just because of the location that I picked. But you can see in our glass brain, again, we're seeing a lot of spottiness. We're not seeing as much activation because of this higher P threshold. But again, we're seeing a lot of spottiness. So what's the best threshold to use? So this is a good question. It depends a lot on what you're looking at and at your task. But in general, if you're going to publish something in fMRI, you need to have a p-value of 0.001. Sometimes you can get away with 0.005 if it's an exploratory study. And our cluster size, we generally restrict to 5 contiguous voxels or higher. So once we've done this, put our voxel threshold, XJView can then analyze these clusters for you and tell you what's contained in each of your clusters. And remember, multiple comparison testing, that's using that family-wise error or that false discovery rate, is often the best approach. These methods, though, are often pretty conservative, and we don't see a lot of activation in those. Okay. So I've put our cluster size to 5 here and our p-value of 0.005 just to show you an example of doing a cluster analysis once we set our thresholds where we want them to be. So once you do this, you can go down to XJView, put your cursor on one of the spots and say pick the cluster. So there's a button there that says pick cluster. And what this will do is it'll tell you how many voxels are in that cluster. So you see here, it's telling you that our cluster size is 110. And it's telling you that now underneath that, total voxels, do you see that? Total number of voxels, 110. It's telling you that 109 of these are in the frontal lobe and 109 are in the right cerebrum. Now, by looking at this picture in some of our planes, it doesn't look like these are all connected, does it? It looks like there's some spots, especially in our axial view. but these are all connected at one point or another throughout the brain here. It's telling you that 63 of these are classified as white matter, and it's telling you that 61 of these are in the superior frontal gyrus. So again, XJ-View has, based on the coordinates and based on prior information, it'll try to tell you where in the brain you're located or where your clusters are located. So that's also a benefit of putting your brain in a normalized space. These programs have the prior information about where the space is and what structures that you'll see if you're at that coordinate location. Another thing you can do here is you can say, go to the maximum point of this cluster, and it'll give you the highest t-value in this cluster. In this particular cluster, this highest t-value is 3.27. It's at the very bottom of this box here. And it'll tell you the coordinate location in MNI space. So this is at a coordinate location of x equals 27, y equals 14, and z equals 49. And these coordinates mean something to people. So when you report something and publish a paper on it, you put these coordinate locations so that somebody else who's looking at this can also interpret where this coordinate is in MNI space. Okay, XJ-View also has some other features. You can say, I want to see all my images in a slice view. It'll give you all your slices. Either you can see here, this is the axial slices. This is, and here is the sagittal slices. So in the axial slices, we're looking at bottom to top. You can see, you can tell at the top here, this is the bottom of the brain, all the way up to the top here at the end. And in our sagittal view, it's going from left to right. So it starts at one ear and goes to the other. Another thing you can do is pick this, what's called a render view, and it gives you this 3D brain with the activation locations on the surface of the brain. Some of the activation that we're looking at is in the midbrain though, so sometimes it's hard to get a good idea about the amygdala and the midbrain structures doing this when you do this. Bless you. Okay, now that we've done our individual subject analysis for this, now we're going to create some group maps to see what happens if we put all our people together with the same contrast. In SPM, I know we talked about some different methods of creating group maps yesterday. What SPM does sometimes is it computes a one sample t-test. So it does a t-test of taking all these people together and computing an average brain for t-values based on this. You can see the calculation there. So it takes the average of all the bold signals from everybody's brains and divides by the standard deviation over the square root of the number of participants in the study. So this is a map here for 114 normal, healthy subjects, all of them looking at the contrast of anger greater than control. And what you see here is that we see a big spot in the amygdala. And I'll show you where that is. So that is particularly in the left amygdala. So that is what we're looking at when we see this brain. So, and this is set at a threshold of p equals to 0.001 and a cluster size threshold of 5. So when we start combining people together, especially for these robust tasks, such as this emotion faces task, we can really start to see what a general activation map looks like in these cases. Sometimes when you look at individual subjects, there's a lot of variability, so you don't get an idea of these big areas where the task is activating by looking at a single subject. On the other hand, sometimes a single subject has really big amygdala activation for this task. So the best thing to do if you're doing an exploratory study, just to find out where the regions of activation are lighting up to your task, you do a lot of participants and then do a group brain like this. So how about if we want to compare two groups of subjects? So what we have here, I'm showing the same contrast of anger greater than control for 32 female genetic carriers. So of the LL serotonin transporter gene. So there's a lot of push right now in the US to study different types of genetic information. And so this just happens to be one such case of this. So in the serotonin transporters, you can have an L allele, an S allele, or and the most prominent is having someone with an L and an S allele. So, and I don't know if you guys have had genetic studies, but you get one from each parent, and these can combine based on what's dominant. So in this case, SL is the dominant type, and so we're looking at people out of these 114 that only had LL or SS. And again, these are all female people. And what we did is we compared LL to SS, looking at this anger greater than control contrast. So what this map here, this is done using a 2-sample t-test. So we've taken a t-test of the 32 people with LL genes and the 32 people with SS genes, 33 people. And this plot is showing only where LL has greater activation to this task than the SS people. And what you can see here, this is again using a threshold of 0.001 and a cluster size threshold of 5. We see basically no activation in this. So we say, well, what's going on here? Well, if we looked here, we see that we're only restricting this to positive activation. So we're only looking at where the LL group was greater than the SS group. Again, we're doing this 2-sample t-test to try to see where if these are overlapping or do actually have differences between them. So what if we turn on the other tail, that SS is greater than LL? Well, here now we can see some activation. So we see that, again, there's some activation in the amygdala, which are these little areas around here. And we see that the SS group has more activation for this particular contrast than the LL group. And this is something that's also been reported in the literature. It's thought that people with the SS genetic alleles for the serotonin transporter are more sensitive to emotional differences, and they typically have more anxiety and attentiveness than the LL group, which tends to be more sort of relaxed to anxious stimuli. So this is indicating that possibly our SS group is having a more reaction to those angry faces than our LL group is. Okay, so finally, I know we need to take a break here, but another type of analysis you could do is what's called region of interest, or ROI analysis. So we could pick a specific area of the brain, and what we could do is we could extract our beta coefficients for this area. So for each person, we take an average of the beta coefficients for each voxel in these areas, and we can compute a mean and a standard deviation of those and compare those across groups to see if one group had a better fit to this task than the other. And those yellow areas here are shown the left and right amygdala. So we might pull out the beta values for this task in the amygdala regions and compare these across participants. Okay, so that's it for this example. And let's take a little break and come back at 11 o'clock. So I've decided, instead of doing our statistical fMRI lecture, issues lecture, that we're going to skip to safety right now, just to sort of mix it up and go for something a little bit more light and easy. If we have time after this, we'll go through the statistical issue problems. And then tomorrow, we're going to talk about DTI, diffusion tensor imaging, and functional connectivity. And hopefully we're going to get into the memory lecture and a little bit about sleep. So the DTI will be a little bit more computationally intensive. I may try to shorten that a little just to give more of a overview in the basics of it rather than the computational details of tensors and computations with that. Okay, so talking about MRI and fMRI safety are some very important things that all hospitals and MRI centers take very seriously, because while MRI is generally considered a safe procedure and non-invasive, it does use this very high magnetic field and these gradient fields and RF pulses. And so if you don't use these or become too relaxed and not attentive, sometimes bad things can happen in these environments. So we're going to talk about safety today. I'm going to show you a few videos of different things, and we're also going to watch the safety video. I was trying to watch it again in my hotel room last night, and it got stuck a few times, so hopefully it'll work a little bit better today. So we'll keep our fingers crossed and hope for the best. Okay, so MRI safety. Again, MRI uses no ionizing radiation, which is a big benefit. People don't have to feel nervous about getting exposed to radiation. Our institutional review boards feel better about letting us study children, letting us study elderly and sick populations. One of the biggest concerns, though, is metal in the body. So all people who are exposed to this MR environment need to be screened for metal in the body. So all people, meaning all the technicians, all the research assistants, all even the janitorial staff, and especially the participants. And we'll see why some of this is so important in a few of the slides to come. All equipment that's brought into the scanning environment must be MR safe. So it cannot have any ferrous metal. It cannot be attracted to the magnet. This could be a very big danger if you bring these into this area. No pregnant women are allowed to be involved in the studies. This is really, it's not known what the effects of a strong magnetic field are to a developing fetus, but for purposes of safety, and I'm not sure about here, but in the US, they're always afraid of getting a lawsuit, so we don't want to cause any harm that is unnecessary, especially in the case of research. There's no life or death situation. There's no reason that they actually have to be in that environment if there's any possible safety concerns or risks. We always err on the side of safety. If there's anything that we think might even be a little bit problematic for a participant, they're excluded from our study. So the field in these MRI machines is so strong that if you take credit cards in there, it's going to erase your magnetic strip on your credit card. It'll also stop your battery in your watch. So you don't want to walk in there with your credit cards in your pocket or anything like that. Every time I walk into the magnet room, I pat my pockets, feel my hair. Even if you know there's nothing, you have to be very careful about going in there. You don't want to get complacent and lazy and just walk in and out. You always want to be aware. The biggest hazards in an MRI machine are, one, the effects of the magnetic and the RF field. So we have this strong static magnetic field. This is our B0 field, going anywhere from 1.5 Teslas to as much as, we use 3 Teslas, but you can go to 7 Teslas, and people are pushing for stronger and stronger magnets all the time. The stronger the magnet, the greater the pull into the magnet. So you want to be very careful. You can get things flying around, and we're going to talk about the missile effect of this strong static field in a few minutes. You also have these pulsed gradient magnetic fields. these are the things that flip to adjust the strengths and make the images. And these gradient magnetic fields can cause currents through different things, because if you remember, we talked about how magnetic fields and electric fields travel together. So by changing these magnetic fields, we can cause currents and different things. So we want to be aware of this. The radio frequency fields can cause heating. So we're injecting energy into a person to flip the protons, but a lot of that energy is dissipated as heat. So we need to be careful of this as well. Some things that we're going to talk about are quenching of the magnet. And we don't talk so much about contrast agents, but if you remember, I talked about gadolinium is used as a contrast agent. And we've seen some cases now, they're starting to be concerned about long-term effects that people might have with exposure to this gadolinium. And patient discomfort, of course, is also a concern. People can get claustrophobic in this environment and panic, and we don't want them to that to happen. We want them to be comfortable. If they feel uncomfortable or panicked for any reason, we want to get them out of the scanner and not continue if they don't feel comfortable continuing. So probably the biggest risk in this environment is the strong magnetic field. So the magnet is capable of attracting ferromagnetic objects with considerable force. We're going to watch a few videos to show how big this force is. But what happens is this magnetic material is drawn very rapidly into the bore of the scanner. The bore of the scanner is where we put the person's head. That's where we try to get the field the most homogeneous. That's where the field is the strongest. So anything that pulls into that scanner is going right for the bore. So we don't want somebody's head to be in there and have something magnetic come and hit them on the head. So we say no metal is to be brought into the MRI environment. And you know that non-ferrous metal won't be attracted to the magnet, but this metal can also heat. So also, when people tell you it's non-ferrous metal, sometimes you're not 100% sure. So if somebody has metal in their body, like a rod or a screw and a bone, we like to get their medical records and the doctor report stating what type of material it is and that it is MR safe. There is a website for MRI safety that if the person knows what type of product they had placed in them, we can look this up, and probably about 80% of the time that product will be listed on there. It'll either be listed as MR safe, MR unsafe, or MR conditional. So MR conditional means depending on the field strength. So higher field strengths can cause more problems in certain types of metal. So we want to take all of this into consideration when we scan somebody. We don't want anybody to bring jewelry in, metal in their pockets, watches, hearing aids, things like this. Leave them completely out of the scanner. If the subject has any potential of having ferrous metal in their body, we do not scan them. I think I mentioned before, people who have worked in metal shops oftentimes have metal shavings in their eyes and they may not even know it. And if we have metal that we're not sure what kind it is, there's always a chance that it can be ferrous metal. So what we do is if we really need this participant, they have some kind of a disorder or a property that we really think they're important to be in our study, we'll send them to have x-rays of their eye orbits to make sure there's no metal there. Metal lodged in bone is not as great of a risk as metal in soft tissue, because metal lodged in bone has more of a hold in place. It's not going to be pulled as easily into the magnet if it is ferrous. So I worked on a study where we looked at about 180 men, and half of these men were violent men, or we were studying psychopathy, and a lot of them had gunshot wounds, and some of them had gunshot wounds they didn't even go to the hospital to have. So if they had any type of shrapnel or we thought there was any problem, we always sent them for an x-ray so that they could, so we could do an assessment and see. We don't know what type of metal it is, so if there's any loose metal at all or any shrapnel in the muscle or the soft tissue, they cannot be scanned. Okay, so the main magnetic field, the static B0 field, can cause projectiles, or what we call the missile effect, into the magnet. You can see somebody holding a piece of metal on a string here. You can see how it's floating there, being attracted to the magnet. Okay. Also here is some kind of a sheet of metal that it's being attracted to the magnet. Here's what happens if you take some kind of metal equipment into the magnet room that is attracted. You end up with a piece of equipment into the bore of this magnet. Here's somebody brought, looks like maybe an IV pole into the magnet. You see it's how it gets stuck there and lodged in. These are cases of hospital beds, how they've been pulled into the magnet, and you can see it's just hanging here. Okay, so I'm going to show you some videos of this missile effect, and let's see. I think one you might have saw at the break. Let's see if this one's going to load. Okay, so this is a 1.5 Tesla magnet. So we use a magnet that is twice as strong as this in our scanning. So watch what happens here. So they have a watermelon here. Okay. That's an oxygen tank being pulled into the machine there. So you can see once it reaches a certain place to the field, it's very quickly pulled into there. So you can see how dangerous then this can be when you get objects in there. Thank you for fixing that for me. So to avoid this missile effect or these attractions to the metal, we also have it's called a safe scan. We can run this up and down about the patient's body, and if they have ferrous metal in their body, it alarms. This is probably similar to what they use when they're checking you out at the airport and things like that. It's not intended to supplement. It's intended to supplement. It's not intended to replace a screening procedure. You'll always need to ask the person and go through a checklist with them. These checklists are usually designed by the center and a safety officer to screen them completely for the metal. And sometimes we ask multiple times. In fact, we scan our same participants 4 times. Every time they get in the scanner, they have to go through this checklist again and have their signature that they confirm that they don't have any of these things in their body. Another problem is the radio frequency field. So the RF pulse that's transmitted, again, is being transformed into heat in the patient's tissue. So this energy is dissipating as heat, and this causes a risk of thermal problems. Okay, so there's this what's called the specific absorption rate of heat. It's a term used to describe the absorption of RF radiation, and if the person is thought to be absorbing too much, they will stop because we're heating them up too much. The FDA in the US indicates MR procedures that exceed a certain specific absorption rate poses a risk to the person. This rate can be calculated based on the person's weight and on the type of pulse sequence that we use. So just to let you know something similar to this, The cell phones or the mobile phones that we have also have limitations on their specific absorption rate when we're holding this to our ears all day. So these are other things we need to consider. Heating and burns. We don't want the person to touch the bore of the magnet. That can also lead to burns. If we have a big person and they're very tightly fit in there, sometimes we'll put padding between their arms and the spores of the magnet. We can also cause burns by inducing electrical currents. So the magnetic fields that are changing from the gradients can cause electric currents. So we don't let the person cross their legs in the scanner, cross their arms. We don't want to make any loops and any wires that we use in there. So we have shock electrodes when we have our participants, and this has a long cord and we try to minimize any types of loops in this cord. Okay, these gradient magnetic fields, again, these changing fields can induce the electrical currents in the conductive devices. We don't want any closed loops. And I'll show you some pictures of some burns that can result after we go through some of these things. Another issue is that these rapidly changing gradient fields can induce nerve or muscle excitation because of the way that the magnetic and electric fields work together. If you remember, our nervous system works on these electric fields. So sometimes a person might report some tingling or something that feels like someone is tapping them. And we usually ask them when they get out of the scanner if they've had any of these negative sensations. We had one guy in the scanner, he was going to have the shock task, and he didn't even have a shock task. And he said, "Oh, you guys have been shocking me." And we said, "No, not yet." And he said, "Well, I feel like you've been shocking me." So we got him out of the scanner. We didn't want him to have any discomfort. He had some other issues as well, so we discontinued his scan after that. At very high levels of these gradient fluctuations in the field, cardiac stimulation is a concern, but these are at much higher changing magnetic fields than what we typically do in MRI. And another issue with these gradient fields is the loud acoustical noise that occurs as as currents pass through these gradient coils very quickly. So the faster that we drive these gradient fields, which in functional MRI, we try to get them to go faster and faster all the time, the more noise that they make. So people get these earplugs and put them in before the scanning starts. Okay, so another issue of safety is quenching the magnet. So what quenching a magnet is this is specific for magnets that use these superconductors. So remember I told you we keep the magnet inside very, very cold. We use liquid nitrogen, and we surround this with inside the liquid nitrogen is the liquid helium. We get this cooled down to almost absolute zero so that we can put a current in a wire, and this current is superconducting at this temperature. So it has very little resistance, and it just keeps going, and that's what keeps this constant magnetic field active. So if we start to raise the temperature inside the magnet, the superconductive property dissipates and resistance occurs in the wire. And what this does is it ramps down the magnet, is what we call it. It creates a loss of the static magnetic field. But as a side effect to this, this heating caused an explosive boil off of the liquid helium. So the helium boils off and it creates a big cloud. This quenching of the magnet can be done in emergency situations. It happens pretty quickly. And these magnets can also spontaneously quench. So like I mentioned before, we've had trouble with one of our magnets. People come in the morning, and for some reason or another, the magnet has quenched in the night. This is a very expensive problem because getting those cryogenics back into working order and ramping up the magnet again can often cost a lot of money to get it going. So this is a problem that we don't want to have of this magnet quenching unless it's a real issue or something's going on. We've had cases of people leaving. So a guy came from FedEx, and he actually left a package inside the magnet room. And this is a very, very big safety concern. But when they came in the morning, this package was in the bore of the magnet. And since they weren't sure what it was, they ended up quenching the magnet. And after they quenched this magnet, this liquid helium boiled off, and it was diverted into the parking lot of the hospital and went all over everybody's car. So it was a very big, a sort of a sloppy way to deal with this. And everybody was, up in arms saying, wow, we should have better regulations than this. So you really have to be careful. You have to consider who's going to be around this magnet. Make sure you have posted signs. Make sure that people are aware, and make sure that when you quench these magnets that it goes into a place where there's not going to be people standing around. So all MRI scanners have a quench button. These are what some of them look like. And ours here looks like the one on the right. So you have to turn a key, open it up, and push that button. You don't want people to be pushing these buttons by accident. It sort of reminds me of this show Deal or No Deal. Have you seen that? Where they offer them money and they can push if they want the no deal. But that's sort of what the button in there reminds me of. You have to open it up and push no deal. But in this case, quench. So we're going to watch a movie when we get things going here to show an example of a magnet quench. So to help with safety control around MRI machines, we have these safety zones in the US. They go from zone 1 to zone 4. So zone 1 is considered an area that's freely accessible to the general public. This might be the reception area where a patient or a participant to be in a research study comes in and are greeted and are screened. Zone 2 is the interface between publicly accessible areas and the zones 3 and 4, which are the more controlled areas. So this might be, for example, a nurse's station that a person passes through to get screened before they go into these zones 3 and 4. Zone 3 is the region in which free access by unscreened and non-MR personnel or ferromagnetic objects or equipment can result in injury. So this is a controlled area. People have to be screened before they enter this zone 3 area. And this is typically where the control room is put, so that our equipment that we run to keep these machines going and run our experiments. Zone 4 is synonymous with the MR scanner room itself. So this is the room in which the MR scanner is confined, and this is the room that is shielded. Now, zones are marked from the bore of the magnet of where the magnetic field starts to drop, so that you have these lines that indicate where the field is less and less when you go away from the magnet. So every MR center should have a map with these zones indicated, so that anybody who's using this area knows which zone is which ones they can bring their participants in without being screened, and which zones people are not allowed to pass into if they have not been screened. And this is taken very, very seriously at our center. So the magnetic room acceptability labels are as follows, and all equipment that's used in this environment are labeled as either MR safe, so they can go into the scanner room with no problems. MR unsafe, which is here. Then on the right, you see nothing that is MR unsafe can be taken into the environment. And MR conditional. So this again is conditional based on a couple different things. So this item has been demonstrated to pose no known hazards in an MR environment with the specified conditions of use. So these specified conditions can include the field strength of the magnet, that static magnetic field strength, the strength of the spatial gradients, and the time rate of change of these magnetic fields as the gradients are pushed to do the imaging location. So there's a lot of different things in this case that needs to be considered. So you look at what type of magnet you have, what kind of pulse sequences you're using to determine if something MR conditional can be taken into your specific environment. So this is a MR safety training video we're going to look at after we get everything working here. And after this, I wanted just to show you a colleague of mine ran the MR Center for a very long time. She's since retired, but she put together this presentation and gave me some examples of what some things that went wrong in magnets due to carelessness or other things that you're going to see. So in 2001, this sort of a freak accident is what they called it. A boy, 6 years old, was being scanned, and he, at the Westchester Medical Center, he was in there, and somebody brought an oxygen tank into the room with him while he was in the scanner. So let's see, officials said that something went horribly wrong on Friday with an MRI test on a 6-year-old boy who had just undergone surgery, even though no metal objects are supposed to be in the testing area, because they will be pulled into the 10-ton machine by its powerful electromagnetics. A metal oxygen tank somehow made its way into the exam room. The tank, about the size of a fire extinguisher, became magnetized and flew through the air and fractured the boy's skull as he was having this scan taken place. So the boy passed away. This was a big wake up to a lot of the people who worked in MRI at how dangerous this missile effect can be. Here's another incident where another oxygen tank was brought into the room. The person suffered a contusion, a partial upper ACL tear of the right knee. This case, they may have been having their knee scanned and not having their head directly in the magnet. So this says that the person didn't require hospitalization or further medical treatment. But again, this is a very serious incident where somebody was being careless and brought in something that was not safe into the MR environment. Okay, here's a report of a member of the cleaning staff bringing in a floor polisher into the MRI suite, resulting in this polisher being attracted to the magnet. The staff member received a cut to the right hand requiring 2 stitches. And let's see, the injured person received 2 stitches and did not require hospitalization or further treatment. So again, these signs are clearly visible, it says, about how you should not take metal into the environment, but people tend to become careless and complacent. And sometimes you have new cleaning staff who aren't informed and completely aware. So you really need to take the time to educate anybody who's going to come into this environment about the dangers of it. Okay, so here's a report where a person, let's see, was positioned in for supine scan with small extremity coil. The patient was touching the bore of the magnet with their shoulder, and they ended up receiving a blister and a burn from touching the bore of the magnet. So this is a case where they should have had some padding around them, and they didn't. Okay, this is a case of an elderly man. He went in to have an MRI scan. His son says his father was told to remove all metal from his body before the MRI, but he was never told anything about leaving his metal walker that he used behind. So when he entered the room, the metal walker was ripped out of his hands and pulled into the bore, and he fell and hit his head on the floor and suffered a stroke from this accident 2 days later, and he died 2 months after that. So this is a case where he was screened very well and checked for no metal in his body, but then nobody thought to think about this metal walker that he was using. And of course, having this ripped so violently out of his hands, can lead to, accidents of other sorts. Okay, this is a case where, so this boy went in, a teenage boy, to have an MRI, and somebody left these EKG electrodes on his chest. So these were metal discs attached to his chest. They weren't removed prior to the MRI. It resulted in heating of these and dime-sized burns on his chest from having the MRI with these leads still on his body. So they were looking for $2 million for pain and suffering and $30,000 for damages. So they were suing this MRI center because of this incident. So this is, again, something you need to worry about, is it burns on the body. Okay, this is an interesting story here. So a lady went into the MRI center to have a scan. She was given a 9-page questionnaire that asked all about metal or foreign objects in her body. She said no to all these questions. She met with the technician, who again went through this, again verbally asked her, and she said no to everything. But she was too vain to tell the technician that she had hair extensions that were placed on her head with metal clips. So when the MRI began, her head and her hair was pulled into all sides of the machine, and her hair began to burn also. So she says she started screaming. The technician could not hear. She was not quick to push the panic button or squeeze the alarm, but once she did, the machine was stopped. And so a massive amount of her hair, along with her hair extensions, was pulled out of her head, and she suffered burns from these. So she sued the hospital in this case. And it says at the bottom here, what women will do in vain for beauty. But we've also had cases of elderly people who had wigs on, and they're too embarrassed to say that they're wearing a wig. And we had one case where we had got the lady into the machine, and there was a big black artifact all around her head, and it was due to this wig that she had on. So even things like this that you may not consider should be thought about before we go into the magnet room. So people now, here's a picture of these magnetic clips that were in her hair. So this was to put hair extensions in. You probably don't have many cases of hair extensions here because the women have such long, nice, thick hair, but in the U.S., people with thinning hair will often put these in to make it look like they have a fuller head of hair. Other things that we need to take into consideration nowadays, they make these contact lenses that change your eye color. They have some kind of a property that aren't compliant with the magnetic field. They also have now that these clothes that contain this silver oxide, it's like a bacterial resistant type of clothing. And so we have to ask about this as well. A lot of times women too will wear makeup with metal in it, like metallic sparkles and things like that, and nail polish. So we also ask about this before our participants go into the scanner. So all the time there are new things to consider as people are developing different types of products. So unfortunately, sometimes it takes the person going in there and something happening before somebody realizes that this product is not MR compatible. Pardon me? Yes, that's a good point. So, yes, fillings. Okay, so fillings, this is a very good point. We always ask about fillings and metal in the mouth. So sometimes too, when people have braces, they'll have a small wire that's left in there to hold their teeth into place to keep them from moving after they've taken the braces out. It's called a permanent retainer. So we always ask about any metal in the mouth. Generally, fillings are not ferrous metal, and they're generally considered safe, but sometimes we have participants come from other countries and we're not sure what type of metal their dentist has used. So in these cases, we won't scan them, especially if it's a very old filling. If it's an older filling that maybe somebody came from China, we're not sure what their dentist used in this case. Another consideration is if they have too much metal in their mouth, it's going to cause this metal artifact, and we're not going to be able to see anything in the image. So this is always something that we address. This issue comes up quite frequently. So again, non-ferrous metal can be brought into the MRI environment. They are not attracted to the magnet, but these non-ferrous metals still interact with the magnetic field and can cause distortions and artifacts in the images. So here's showing some of what these artifacts might look like. So here's some dental work artifacts here. You can see it's causing these black holes and these funny looking shapes of the head. Here's somebody with braces on the far top right here. You see it's just a big black hole in their head. So when you're looking for functional imaging, you don't want to scan somebody like this. You're going to end up with a lot of missing data. This was a big issue when I was scanning teenagers. I would call and exclude a lot of people because they had braces. And this is a prominent age in the U.S. when kids get braces to fix their teeth, early teenage years. We interestingly had people that would swear up and down they had no metal. We asked specifically about braces. No, we don't have braces. The kid would come in and he'd smile real big and he'd have braces on his teeth. So it's like, all right, so sometimes you screen people over the phone and they want to be in your research study so badly because they want the money that they just don't tell you things too. So when they come in, it's very important to go over these screening procedures again. In cases like braces, it's pretty apparent that they have them, but you really have to be very vigilant and diligent about these screening procedures. Here is a person wearing a wig. I'm not sure what was in this wig, but you can see that you really can't see any of the brain in this case. And this was some kind of a facial repair here. Okay, so here's some burns that are caused by MRIs. So this one here on the bottom right was caused by a loop, a current through a loop. So this person, I think this is maybe some part of their body where it was touching during the scan, and this induced a loop and caused burn here at the points of the skin. So you really have to tell people, please don't cross your legs if they do it. Some people just feel more comfortable with their legs crossed, and we have to keep a watch on them and say, please keep your legs uncrossed. Here's another burn at the top left. I'm not quite sure what that was caused from, but it was an MRI-associated burn. Another issue that we deal with in the U.S. is tattoos. So some of the older tattoos that people have, or if they got a tattoo while they were in prison or somewhere where a standard technique wasn't used, sometimes they have metal in them. We've had people that had scans with tattoos where the metal in the tattoo actually pulls towards the magnet, and it results in irritation to the tissue and burning. So here's some cases where burns were resulted from having tattoos. So that's another thing that we have to ask about and consider when we do these scans. All kinds of problems that you would never think about. Okay, so that's the end of the safety. Should we take a break? Or I want to play the videos. Okay, this shows. Whoa. Still playing, I guess, here. Okay.
Whoa!
Is it too loud? Is it okay?
So the force we're reading on that guy right now, just at that part of the magnet, is close to 300, 280.
Okay, this is a controlled quench. Okay. They're doing this purposely.
No. 400 now.
And it's going to attach itself to the board.
10, 9, 8, 7, 6, 5, 4,
He's excited.
3, 2, 1. He's giving us a reading of 500 pounds.
The flip start?
Here it comes, it's going.
Oh, wow.
Liquid helium boiling off there. So.
We are at 700.
There it goes.
Yeah.
700 pounds.
That was cool.
Oh! And we have jumped to 1,300.
That's going to be on that's exactly everything.
Yeah.
Most everything's a fall out.
Oh, yeah.
So we're just about to hit the switch.
Fog
But
going up.
fog up the ceiling. Baby.
There we go.
Okay. Yeah, look at it. 1,700.
We are at 1,700, which is far more than this.
1,800.
1,800.
It's past the
No, we're going to
There you go.
This.
Oh,
It's liquid oxygen, liquid nitrogen.
got cold enough to actually.
Yeah, it's liquefying on the steel. It's actually liquefying on the steel. You hear it if it sounds hot. It sounds like it's popping.
Oh yeah,
That's,
you
that's,
can.
that's liquefied air.
It's all coming down and.
Yeah, you burn yourself big time if you get near that.
Yeah, you burn yourself big time.
We can probably use it.
Just talk to me. We can put it aside. We're just going to start tying it up. So there's no rush. We'll just keep the dibs on.
So when should we come take it? Like, we just
Take it.
Yeah.
Okay, so that was a 4T magnet that they ramped down. So you can see there's a lot of things that was happening there. The biggest, of course, being this liquid helium boiling off. And you can see that they said that it was so cold that it was liquefying the air as it went out. And that's a lot of money of helium there, liquid helium that's boiling off. Because I believe that helium is getting more rare in nature, and that's what we are told in the U.S. anyway. Why our balloon prices are going up if you get some balloons, so it becomes more expensive as it does so. So maybe this would be a good time to take a break, and then when we come back, we can watch the safety video. If you guys want to do that, this is the video that we all have to watch for safety training before we are allowed to go into the field, and we have to do this every year so that we can maintain our safety credentials to be able to work in this environment. Okay?
This program was developed to help you understand essential and vital information pertaining to the use of MRI technology. My name is Frank Shellock. I'm an adjunct clinical professor of radiology at the University of Southern California, and I've been involved in the field of magnetic resonance imaging, or MRI, for more than 25 years. One of my primary areas of interest is to educate and to train healthcare workers and other individuals concerning the importance of ensuring a safe MRI environment. The MRI environment refers to the area in and around where the MRI system or scanner is located. To ensure your safety and to protect others, all individuals who need to enter the MRI environment on either an occasional or regular basis must undergo proper training regarding the potential hazards and dangers that are associated with this area. It should be noted that while many MRI safety issues exist, the information presented in this program specifically emphasizes the aspects of the MRI environment that directly impact those of you who occasionally or periodically enter this area. Please be advised that this program does not replace any special policies and procedures that may exist at your facility. Nevertheless, it does provide you with extremely useful information that will help you to preserve a safe MRI environment. After completing this training program, you'll gain an appreciation for the importance of MRI as it is used as a diagnostic imaging technique. You'll be able to identify the hazards associated with the MRI systems and the MRI environment, and you'll have an understanding of the screening process that is required to complete before you are allowed into the MRI system room. Importantly, you'll be able to describe the steps to take in order to prevent accidents and injuries in the MRI environment. Magnetic resonance imaging, or MRI, is a diagnostic imaging technique that produces images of the body without the use of ionizing radiation. The MRI examination requires specialized equipment that includes an extremely powerful, constant, or static magnetic field, rapidly changing local magnetic fields, the use of radio frequency energy, and dedicated equipment, including a powerful computer to create very clear images of the body. With proper safety procedures and guidelines in place, MRI poses no known permanent side effects to patients, medical personnel, or other individuals. However, serious injury or death can occur, and the MRI system may sustain damage if safety guidelines and screening procedures are not carefully followed. Here's a diagram showing the basic parts of a typical MRI system, which may also be referred to as the scanner. Note the most important components of this system, which include the extremely powerful magnet, the gradient magnet coils, which generate rapidly changing magnetic fields, and the radio frequency, or RF coil. Magnetic resonance imaging is commonly used to image the brain, spine, and joints, such as the knee, ankle, and shoulder. One of the important things for you to remember is that even when the scanner is not operating to image the patient, the powerful static magnetic field is always on, and therefore, the potential hazards and dangers associated with the scanner's magnet are always present. If you enter the room where the scanner is located, you'll be exposed to that powerful magnetic field. Accidents often happen because individuals assume that the magnetic field of the scanner is off because it isn't being used to image a patient, and then they mistakenly bring inappropriate metallic objects into the room. Therefore, you should never enter the area of the MRI scanner room without permission from an MRI technologist, radiologist, or other healthcare professional that has undergone proper safety training that involves comprehensive education over and above what exists in this basic MRI safety training program. Various types of MRI systems exist, and they are typically categorized in terms of the strength of the static magnetic field. Commercially available scanners range from 0.2 to 3 Tesla, with the most commonly used MRI system operating at 1.5 Tesla. The highest field strength scanner currently used in the clinical setting is the 3 Tesla MRI system. MRI scanners can be found in a variety of settings, including hospitals, outpatient clinics, doctors' offices, operating rooms, interventional suites, and university research centers. Therefore, it is important for you to be prepared for each instance where you may find an MRI system, because each setting can present entirely different safety issues. Well, the term MRI environment generally refers to the area in and around where the scanner is located. This includes the MRI system room, which is often referred to as the security zone, as well as the scanner's control room, which is where the equipment is located for the operation of the scanner. This is where the MRI technologist is typically found. The MRI environment also includes any area where there may be substantial magnetic fields associated with the scanner, or the area that contains the fringe field. Depending on the design of the MRI facility, the magnetic fringe field can extend well beyond the room, above and below the scanner. So the term MRI environment really refers to all of the physical areas where the influence of the scanner may be felt, especially with regard to the magnetic field of the system. In order to prevent incidents and accidents associated with the MRI environment, MRI facilities implement a variety of techniques to control access to this area. Of course, one of the most important ways to control access to the MRI environment is to have an MRI safety-trained individual monitoring the area and preventing entry by unauthorized individuals. This MRI safety-trained staff member is particularly concerned with keeping unwanted objects far away from the MRI system. Other techniques to ensure safety in the MRI environment include the use of special door locking mechanisms to control entry to the room, and to prominently display danger signs that are usually located in and around the MRI entrance. Some MRI facilities also utilize special metal detectors that are capable of identifying magnetic objects which are well known to pose potentially serious hazards in the MRI environment. Also, certain MRI centers have implemented a zone method as described by the American College of Radiology. Here are examples of the signs that you will see posted in and around the MRI system room and/or in the MRI environment. Notice that these signs clearly state the words danger, this magnet is always on. As I previously mentioned, some MRI facilities also use specially designed metal detectors called ferromagnetic detection systems that can identify magnetic objects in order to help prevent accidents and injuries. MRI facilities may also implement the zone technique with posted signs and physical barriers or other methods to control access to the MRI environment. Zone 1 is the area that is freely and readily accessible by the general public. Zone 2 is typically the place where the front office staff or receptionists are located. Zone 3 is the control room area, and importantly, only personnel, patients, and other individuals supervised by MRI safety-trained personnel are allowed in this area. And finally, Zone 4 is where the scanner is located. Now I'd like to further discuss the fringe field of the MRI scanner because it is essential that you understand that this magnetic field extends out from the MRI system in all directions, including in front of and behind the scanner and above and below the system. And this fact has very important safety implications. As you move closer to the MRI system, the strength of the magnet increases substantially, and this factor is responsible for creating one of the most hazardous situations in the MRI environment, which is the missile effect. The powerful magnetic field of the scanner can attract certain metallic objects, causing them to move suddenly and unexpectedly, and with great force towards the center of the MRI system. Obviously, the missile effect can pose a substantial hazard to anyone in the path of a flying projectile, as well as to the patient if he or she is inside the scanner. Here is an example of the missile effect showing the magnet of the MRI system attracting a pair of metallic scissors.
The scissors were attached to a strong string and then dangled in front of the scanner. Notice the initial position of the scissors positioned about 8 feet from the MRI. System. As the scissors are moved closer, they are quickly and forcefully attracted by the magnetic field. Now carefully watch the scissors as they are brought closer to the.
Obviously, the missile effect can pose a substantial hazard to any, as well as the temporary loss of the use of these important imaging systems. Now here's an example of an extremely large hospital bed that has a large number of magnetic parts becoming a projectile, and now it is firmly attached to the powerful magnet of the scanner. This accident and the prior ones illustrate the serious hazards of taking inappropriate patient transport devices into the MRI environment. You should only take items such as wheelchairs, gurneys, stretchers, and other similar devices into the scanner room that have been specially designed to be acceptable for use in the MRI setting. Over the years, missile-related accidents have been responsible for serious injuries to patients and other individuals and have caused at least one fatality. Important guidelines that you should follow to prevent missile or projectile-related accidents include the following. First and foremost, you must undergo proper MRI safety training and repeat this training on a regular basis, such as once each year. Additionally, you should routinely review all MRI safety policies and procedures set forth by the MRI facility and make sure that you ask an MRI safety trained healthcare professional if you need clarification or further explanation about any matter. You must understand that the powerful magnetic field of this MR system is always on. Never allow equipment, devices, or other objects containing magnetic parts into the MRI environment. You should only use patient transport devices such as wheelchairs, gurneys, and stretchers that have been specially designed and approved for use in the MRI environment. Before you are allowed into the MRI environment, you must undergo a screening procedure to ensure that there are no problems or issues that might pose a danger to you in this setting. Because the majority of MRI-related incidents have been due to deficiencies in screening methods and/or the lack of properly controlling access to the MRI environment, especially with regard to preventing personal items and other potentially problematic objects from entering the scanner room, it is crucial for MRI facilities to have procedures and guidelines in place for screening in order to prevent accidents. So exactly who needs to undergo MRI screening? Well, basically, everyone who will encounter the MRI environment. Why is it necessary to do comprehensive screening for both patients and other individuals? Well, as I've previously indicated, MRI technology uses a powerful static magnetic field, rapidly changing magnetic fields, and radio waves or radio frequency energy. Each of these may pose issues for patients and other individuals in the MRI environment, and more importantly, for anyone who's in the scanner room or inside of the system while it is operating. Remember, the static magnetic field of the scanner is always activated, and therefore the hazards related to this powerful field are always present. Of further concern is that for individuals and patients who may have certain implants or devices, the powerful magnetic field may interfere with their operation or pose problems if the item is strongly attracted by the magnet. In addition, the scanner's magnet can permanently damage certain implants as well as personal items such as cell phones, mechanical watches, and hearing aids. During the operation of the MRI system, the patient is exposed to rapidly changing magnetic fields that are generated as part of the imaging procedure. These so-called gradient magnetic fields can stimulate nervous tissue in patients under some operating conditions. However, this rarely occurs during magnetic resonance imaging. In addition, currents may be induced in certain implants and devices, and therefore, part of the screening procedure is used to determine if there may be problems related to scanning patients with these items. The rapid changes in the magnetic fields can also cause minute expansions and contractions of the magnet coils, resulting in vibrations that can produce loud noises during the imaging procedure. Therefore, hearing protection is provided to the patient in order to prevent issues related to the loud noises that may be associated with the MRI examination. Importantly, if you must remain in the scanner room while it is operating, you should also wear proper hearing protection such as earplugs. The MRI examination also involves the use of radio frequency energy or radio waves, which are delivered by means of the radio frequency or RF coil. The patient's body part contained within the RF coil may experience an increase in temperature under certain MRI operating conditions. If the patient has a metallic implant, it could also heat during the examination under certain operating conditions. Therefore, part of the screening procedure as it applies to patients addresses the possibility of tissue and/or implant heating that may occur during an MRI procedure. Now let's take a closer look at what is actually involved with the MRI screening procedure. During screening, you'll be asked to fill out a form that poses important questions to determine if there is any reasons why you should not be allowed to enter the MRI environment. Other questions will be asked to determine if you have any implants or devices that could be hazardous to you if you go into the scanner room that houses the scanner. After you fill out the screening form, an MRI safety trained staff member will conduct a verbal interview that gives you the opportunity to discuss information on the form and to verify that you understood all of the questions. If you have any question or concern regarding your safety in the MRI environment, please consult the MRI technologist, radiologist, MRI safety officer, or other MRI safety trained staff member. Before entering the scanner room, you must remove all metallic objects, including pocket knives, nail clippers, your wallet, your watch, and jewelry. Besides being attracted to the magnetic field of the scanner, objects such as hearing aids, cell phones, and mechanical watches may be damaged. Also, exposure to the magnetic field can erase magnetic storage media such as bank cards, credit cards, and identification cards. Therefore, these objects are not permitted in the MRI environment. When bringing devices and equipment into the MRI system room, especially in response to an emergency, make sure ahead of time that they are not attracted to the magnet and that they were specially designed to be used in the MRI environment. Obviously, this should be done well in advance of the time in which they may be used, and they should be clearly labeled to indicate that they are non-magnetic, MRI safe, or MRI conditional, which indicates that they are appropriate for use in the MRI area. Here's an example of a footstool with a proper label on it indicating that it is non-magnetic and therefore it can be safely used in the MRI system room. You may also see other labeling icons or symbols on devices indicating that the item is either MRI safe or MRI conditional. Items with these labels can be utilized in the MRI environment, although the label MRI conditional means that specific conditions must be met to ensure the item's safe use. Therefore, please consult the MRI safety trained staff member regarding the proper use of any item with an MRI conditional label on it so that you understand the conditions that are acceptable for its use. Unfortunately, there are many commercially available devices including wheelchairs, gurneys, IV poles, instrument stands, oxygen tanks, laundry carts, cleaning devices, and tools that are made from materials which allow them to be safely used in the MRI environment. Physicians, nurses, pharmacists, respiratory therapists, and other hospital staff members must remember to remove all personal items and to empty their pockets before entering the scanner room. MRI facility engineers, construction workers, and others must use non-magnetic tools and other equipment designed specifically for use in the scanner room. If you are a custodial worker, be aware that you cannot bring many of the conventional cleaning supplies and equipment into the MRI system room, especially large devices like floor buffers and vacuum cleaners. An MRI safety trained staff member will provide you with specific information regarding how to clean the MRI environment as well as what type of equipment you should use in this setting. Security and police officers must remember to remove their equipment belts, holsters, guns, bullets, handcuffs, flashlights, pepper spray, communication devices, and other similar objects before entering the scanner room. The MRI scanner and the MRI environment present special challenges to firefighters, mainly because of the presence of the magnetic field. Most standard firefighting equipment, including respirators, axes, crowbars, and fire extinguishers, are magnetic and therefore unsafe for use in this setting. Other problems exist as well. Because of these issues, it is vital to be prepared well in advance to ensure that there are no problems or accidents. it is very important to have a planning meeting with the manager of the MRI facility to discuss proper procedures in order to be best prepared for firefighting or other emergency situations. MRI facilities must develop and regularly practice an emergency plan that explains the critical activities for staff members, defines the use of special equipment, and that addresses other pertinent issues related to medical or other emergencies in order to ensure MRI safety. It is especially important for the patient to be removed from the scanner room prior to the arrival of an emergency response team, so the MRI facility must have a carefully planned and rehearsed procedure in place to accomplish this task. Healthcare professionals who are members of the cardiopulmonary resuscitation or Code Blue team must be specially trained and prepared to conduct their activities in the MRI environment, with an emphasis on removing the patient from the room as quickly as possible so that patient management occurs at a safe distance from the scanner. For outpatient or mobile MRI facilities, it is necessary to provide prior education to outside emergency personnel such as paramedics and firefighters regarding the potential hazards associated with the MRI environment. Important recommendations related to emergencies in the MRI environment include the following. Make sure you understand and follow all site-specific MRI safety policies and procedures. Also, be prepared in advance for emergencies and other problems that might occur in the MRI environment. Do not take unauthorized equipment or other unsafe devices into the scanner room. In serious cases, it will be necessary to quickly remove the patient from the scanner room. Once this is done, it is best to secure the room to prevent unintentional entry into the MRI system area. If the scanner does not have a detachable table, an MRI safe or MRI conditional gurney or stretcher must be readily available and close by. During the emergency, follow the instructions from the MRI staff members. As I previously mentioned, there is a possibility for a rather large magnetic object to become a projectile if it is brought too close to the MRI system, resulting in it being firmly attached to the scanner. Additionally, it is possible for an individual to be trapped between the magnetic object and the scanner, which obviously presents a serious emergency situation. In the event that something like these incidents occur, it may be necessary for an MRI staff member to decrease or ramp down the magnet of the scanner by means of a procedure called a quench. A quench is a sudden loss of the magnetic field of the scanner if it utilizes a superconducting magnet. This involves the venting of extremely cold materials known as cryogens. Liquid helium is the typical cryogen that is used to cool down high field strength magnets used by MRI systems with superconducting magnets. When a quench occurs, the cryogen, which normally exists as a liquid, turns into a colorless and odorless gas. The escaping gas appears as a vapor cloud, and an extremely loud noise may be produced. There are two types of quenches, controlled and uncontrolled. A controlled quench is used when there is a planned removal or ramping down of the magnetic field. An uncontrolled quench, which is a rather rare event, occurs if there is a problem or defect in the magnet that causes an increase in the temperature of the cryogen. With both controlled and uncontrolled quenches, the escaping gas is typically vented out of the MRI system room. However, venting systems sometimes do not work properly or they simply fail. If this occurs, cryogen gas can accumulate in the scanner room, and this can create a dangerous situation. If a quench occurs, you must avoid being exposed to the escaping cryogen gas because exposure to this gas can cause a loss of consciousness. Therefore, all individuals must evacuate the magnet room before a quench or as soon as possible after the quench begins. Since different MRI facilities have different procedures to follow depending on the specific type of scanner that they may have, please review the safety policies related to a quench with your MRI facility manager or other qualified MRI personnel. Because a quench sometimes has undesirable or dangerous effects, only authorized, specially trained personnel are allowed to perform or initiate a magnet quench. In addition to viewing the content of this MRI safety program, I invite you to visit the website www.mrisafety.com, which is a valuable source of information pertaining to all aspects of MRI safety. In general, MRI is a very safe diagnostic imaging procedure. The relatively few problems that may occur are mostly related to bringing potentially dangerous metallic or other inappropriate objects into the scanner room, or due to the accidental exposure of patients or individuals with certain types of implants to the electromagnetic fields of the MRI system. I encourage you to actively participate in the safety program at your facility by helping to inform and warn others about the potential hazards of the MRI environment. Remember these important points. The magnetic field of the MRI system is always on, and dangers always exist, even when a patient is not being imaged. If you enter the MRI system room, you will be exposed to the powerful magnetic field. You must undergo an MRI screening procedure before being allowed into the MRI system room. Remove all metallic objects, personal belongings, and other items before entering the scanner room, and empty your pockets. Make sure that emergency and other equipment is non-magnetic or otherwise acceptable for use in the MRI environment. Follow all written and verbal instructions provided by the MRI staff members. And finally, if you have a question or concern about any MRI safety matter, please discuss this with an MRI safety trained professional. Congratulations on completing the basic MRI safety training program. You should now have an understanding about the important safety issues and possible dangers associated with the MRI environment.